Hello world.
Today, I'm going to tell you about full-wave rectifiers. You might be wondering, what the heck is a full-wave rectifier? Remember from the video on half-wave rectifiers that half-wave rectifiers take an AC signal and make it look like this. Here are the input and output voltage signals from the half-wave rectifier to jog your memory. The half-wave rectifier only allows portions of the negative or positive part of the wave to pass through and power our device. In this case, we have only allowed positive portions of the wave to pass. The problem is, our device sits idle during the negative portion of the input signal. We are wasting all of that negative energy. This is very inefficient. To harness the energy from the negative and positive portions of the input signal, we use a full-wave rectifier. A full-wave rectifier will do everything a half-wave rectifier will do, and it will also take the rejected portion of the wave and flip it so we can use it. Here's what a circuit with a full-wave rectifier looks like. The AC voltage supply on the left is like the power company. Diodes 3 and 1 do the rectifying, while diodes 2 and 4 are needed to further direct the current. The resistor represents the device that we want to power. Let me show you how this works. Let's redraw the circuit so it's not so confusing by moving the resistor without changing any of the nodes. You can pause the video and verify for yourself that all of the connections are still the same. Remember that conventional current can only flow through the diodes in the direction that their triangle points. Assume that the voltage becomes sufficient enough to switch all of the diodes in the path of the current on. For the sake of this video, we will call current produced during the positive portion of the signal positive current. It flows from the upper terminal of the power supply. We will call current produced during the negative portion of the signal negative current. It flows from the lower terminal of the power supply. Let's begin. We will first assume that the reverse saturation current for the diodes is negligible and come back to that in a minute. When the voltage from the power company is positive, current flows out of the upper power supply terminal to node A. From there, it flows through diode 3. Diode 3 does the exact same thing that the diode in the half-wave rectifier does. From diode 3, the current travels through the resistor to node B, and then through diode 4 to the lower terminal of the power supply. You might wonder why, at nodes B and C, no current traveled through diodes 2 and 1, even though the direction of their arrows indicated that it could. This is because node A is at a higher potential than node B, and node D is at a higher potential than node C, so diodes 2 and 1 are in reverse bias. For our purpose, we're going to pretend that no current could flow through them because it would be like water flowing uphill. But in reality, a very small current called the reverse saturation current flows through them. But only computers and electrical engineers have to worry about that. When the voltage from the power company is negative, current flows out of the lower power supply terminal to node C. From there, it flows through diode 1. Diode 1 flips the current by directing it to node D, where it must flow through the resistor in the same direction that the positive current did. This means that at node D, the negative portion of the input signal has become identical in sign to the positive portion of the input signal. From the resistor, the current goes to node B. However, unlike the current from the positive portion of the signal, it does not go through diode 4 to the lower terminal of the power supply. It goes through diode 2 and node A to the upper terminal of the power supply. The reason for this is, with the higher potential actually being at the lower power supply terminal in this case, diode 4 is in reverse bias. You may have realized by now that diode 3 is also in reverse bias in this case. We now have a full-wave rectifier. Our device can make use of the negative and positive portions of the input signal. But wait! Look how choppy the signal is. We say the signal has a big ripple. Most household devices need direct current to run, and this signal's ripple is too big to be considered direct current. In the next video, we'll show you how to fix this by making an AC to DC power supply.
Goodbye.